example number 3, the portion of the curve x equals 2/3 y to the 3 halves between y equals to 0 to y equals to 3 is rotated about the x-axis. Find the area of the resulting surface. Well, so notice in this case we have something different this time. So this time we have number 1, function of y. We're given limits in terms of y as well. But this time we're rotating, we're not rotating the region about the y-axis, we're rotating it about the x-axis. So number 1, let's graph. Let's graph the function. So, well, that graph looks like this. I'll just give you the graph. And we're rotating it about the x-axis. This will give us the following result. Alright, that's going to be the solid that we would be obtaining here. Alright, so in this case, well, number 1, let's write down a formula for the surface area in terms of y. So that's 2 pi still integral from c to d, not from a to b. And this r of x will become r of y times the square root of 1 plus the function, the derivative of the function of y squared with respect y. Alright, so let's define how we're going to set up the integral. Well, this r of y, which is usually the tricky part of the problem. Well, so number 1, let's draw that radius. I'm going to use this red line. And that radius should be the distance from the axis of revolution to any point on the graph that we are rotating. In this case, well, this is a vertical line. Alright, that's a vertical line. Well, in this case, a vertical line, what variable is used to describe vertical distances here? Y, right? So it's in the y direction, so it's vertical. So that means this r of y equals to y. But in this case, we are not going to replace this y with, well, f of x, because no, we're not working with functions of x this time. We're working with functions of y. So y is already y. Alright? But still we need to find the derivative of this function. That's x equals to 2/3 y to the 3 halves. This x is going to be our f of y. So that's f prime equals 3 halves times 2/3 of y to the 3 halves minus 1. That's y to the 1 half. Cancel the 3's, cancel the 2's. That's the square root of y. So that's going to be here. Alright, so number 1, let's write down our integral, and make some space, and this will become the integral, or rather 2 pi, the integral from c to d, in this case from 0 to 3, of y times the square root of 1 plus the derivative of the given function, which we got to be the square root of y, quantity squared dy. Well, so let's simplify this integral a little bit, and in fact we can, because the radical will get cancelled by the square, because those are inverse operations. And what else? So let's write what we are left with. That's 2 pi integral from 0 to 3 y root of 1 plus y. Alright, so let's talk about this integral. So again, every time we want to use the method of, what's that? Well, the method of substitution. Oh, it's my battery. Okay. Yeah. So typically we'll look for the pattern, whatever is inside. Okay, whatever is inside of the radical, parentheses, a trigonometric function or logarithmic function or the exponent of an exponential function to be 1 degree higher than what it's multiplying the dy, because, well, when we take the derivative, those two powers are going to match, and that's going to stand the u du part of the problem. So that's the usual pattern we do when we're trying to do the u substitution. Now, if you observe this integral 1 plus y inside of the radical, this is not 1 degree higher than what we have outside, right? In fact, they're the same degree. If we find the derivative of 1 plus y, we're going to get something of degree 0, which doesn't match the degree of what we have outside. And, well, we're still going to use a u substitution in this case. And you might have seen this substitution example, or this substitution cases back in Calculus 1. It's not going to be the usual 2-ingredient u du substitution. It's going to be a 3-ingredient one. So number one ingredient, number 2 ingredient. I'm going to write the third one in a second. So again, u equals to 1 plus y du equals to dy. So no correction factors at all. That's going to be fine. And that third ingredient is, in this case, to solve for y. That's u minus 1. And that's number 3. So and as well, let's also change the limits of integration. U of 0, u of 3. So u of 0, that's 1 plus 0, and 1 plus 3. That's going to be 1, that's going to be 4. So let's do the substitution. Let's go back to the integral. So that's going to be 2 pi integral from 0 to 3. And that's, well, number 1, we had a substitution for y, and this y will be u minus 1, and square root of 1 plus y, that's the square root of u du. Oh, I didn't change the limits, 1 to 4, and that's 0 to 3. And, well, so in this case, having this third ingredient in the substitution is going to help us, because we're going to distribute this and get a sum of two terms. So that's 2 pi integral from 1 to 4 of u minus 1 u to the 1/2 du. And what we're going to do here is distribute the u to the 1/2 to the two terms that we have here. Well, that's going to be 2 pi integral from 1 to 4 u to the first times u to the 1/2. That should be u to the 3/2 minus u to the 1/2 du. This will be, well, let's just use the general power rule to integrate these two. Well, add 1 to the exponent to each and divide by that new exponent. So that's 2 pi u to the 5/2 over 5/2 and minus u to the 3/2 over 3/2, and that evaluated from 1 to 4. So let's see, what's this? So number 1, let's clean up these madnesses right here for a second. So number 1, the dividing by a fraction is the same as multiplying by the reciprocal. In this case, that's going to be 2 pi 5/2 u to the something. Well, that's u to the 5/2 and minus 2/3 u to the 3/2. But how about in this case? Well, I'm going to go back to radical notation here. So, but there's something where, yes, 2/5, yes, 2/5, and that's true. Thank you. Yeah, I didn't flip the first one. So, right here. So this u to the 1/2 and u to the 3/2. Well, let me just look at the u to the 5/2 case. It's going to be the same for the other one anyway. So this means the square root of u to the 5th power, and this also means the square root of u, the whole thing, to the 5th power. And, well, in some cases it will be more convenient if you want to use one version or the other version. In previous problems, like in arc length, we used the first version because we got the limits of integration not being perfect squares. So in this case, what we did is play with the powers, take out the perfect squares, and simplify as a radical in exact form, not in approximated general form. Well, the second version is useful when the limits of integration are perfect squares, because in this case, well, we can easily take the square root of 4 and the square root of 1 and then raise to the 5th power instead of doing the square root of 4 to the 5th power, which I don't know what 4 to the 5th power is, and on a quiz or an exam you're not going to have a calculator to compute this quantity. So it's important to take into consideration which of these two versions of the radical property is the more appropriate. Yes?
So that's what we did when we had y times the square root of 1 plus y. So if we did, we rewrite it as y times 1 plus y plus 1/2, and we should do the y that way.
Yeah, that's essentially what I did later. I wrote it to the 1/2 and then distribute.
Okay.
Yep. And so we're going to go with the second version in this case. Alright, so that's going to be then the square root of u to the 5th power, the square root of u to the 3rd power, and evaluate it from 1 to 4. Well, so this will be, I'm not going to give it enough space. Okay, let me continue here. So that's 2 pi. So that's 2/5, and times the square root of 4 to the 5th minus 2/3 square root of 4 to the 3rd. That's the plugging in for the upper limit, and then the other limit, the lower limit, will be 2/5 root of 1 quantity squared minus 2/3 root of 1 to the 3rd power. We need to compute all this. Well, the second term is really easy to simplify. Well, that's going to be just the square root of 1 times whatever coefficient here, but first let's do 2 pi, and well, so square root of 4, which is 2 to the 5th power is 32. 32 times 2/5, that's going to give us 64 fifths, minus the square root of 4, which is 2 cubed, and that's going to be 8 times 2, that's 16 thirds. So that's the first term. The second term, well, square root of 1, which is 1, and to the 5th, and then cube, well, it's going to be just 1, so that's just going to leave us with 2/5 minus 2/3. Alright, so let's simplify one at a time. Well, I thought I had the final answer here in my notes, but it looks like I'm missing this page right here, so I'll have to do this by hand. And well, so 64 fifths minus 2/5, this is 62 fifths. And negative 16 thirds minus negative 2/3, that is plus 2/3, that's negative 14 thirds. Alright, so in this case we will need common factors to simplify this fraction. So multiply by 3, multiply by 3, multiply by 5, multiply by 5. So 62 times 3, I'm going to do it by hand. 62 times 3. Oh, come on. So 6 and 18, 186. And so 186, and then 14 times 5, that's 70. So two pi times 186 minus 70 over 15, and 186 minus 70, isn't that a 116? That equals to 2 pi times 116 over 15. But well, 116 times 2, that's to 32 over 15 pi. And that's final answer for this integral. Right? Yes, crazy numbers, that's what this kind of problems give us. Weird numbers with results. And for the last exercise for this section about surface area. So what are we going to do next? So we're given the arc of the parabola y equals to x squared. Well, let's start plotting that parabola. But in this case, we don't want the whole parabola. We just want the part of the parabola that goes from the point 1, 1 to 2, 4. Well, in this case, we want to rotate this graph about the y-axis. That's going to give us as a result this solid right here. Alright, so that's the solid that we obtained. It's a revolution about the y-axis. So let's see. Number one, let's set up an integral that from 1 to 2. Well, so what we're going to do is do the same problem twice. When we do the same problem twice, in this case, the first way, as a function of x, and we're going to do it a second time as a function of y. Alright, so, well, number one, so we're rotating this region about the y-axis. That means that radius r, when we set up the integral, so s equals to 2 pi integral from a to b, because it's functions of x, r of x, square root of 1 plus f prime of x, quantity squared, with respect x. Well, so in this case, from the axis of revolution to any point on the graph that's rotating, notice in this case we have a horizontal distance. So in this case, which variable describes horizontal distances? Isn't that x? So that means in this case r of x is x, but in this case we're not going to replace x with f of x because it's already an x, because it's an integral in terms of the variable x. So, well, what do we need to do? Well, let's find the derivative of the given function y equals x squared. Oh, that's an easy one to find. That's just 2x. So that's going to give us the following integral. So that's 2 pi integral from a to b, in this case from 1 to 2, because we're given ordered pairs this time. So if we are evaluating an integral in terms of x, we're going to use the x values of the given order pairs. That's going to go from 1 to 2. So that's r of x, which is x, square root of 1 plus the quantity 2x, which is the derivative of the function, squared. And be careful, because a very common mistake when simplifying a quantity like this is to either forget to square the 2 or forget the x, or forget to square the x. And in this case, this power 2 is affecting both the 2 and the x. So 2 pi integral from 1 to 2, that's x square root of 1 plus 4 x squared. Alright, well, so let's look at this integral. What would be a good method to evaluate this integral? Use up, right? I think it's a good one for use up. So, well, so u equals 1 plus 4x squared, du equals 8x dx, that means x dx, equals 1/8 du. And also we need to change the limits, u of 1 and u of 2. So that's 1 plus 4 times 1 squared, 1 plus 4 times 2 squared. So 1 squared is 1 times 4. Well, that's 4 plus 1, that equals to 5. And 2 squared, which is 4 times 4, that's a 16. And 16 plus 1, isn't that a 17? Well, so let's go back to the integral. That's 2 pi integral from 5 to 17 of x dx, which becomes 1/8 du, and the square root of the quantity u, which in this case is the expression that we got inside of the parentheses, which we set u to find the du. So there's a couple of things that we might want to do. Take out this 1/8 out of the integral and multiply, reduce it with the 2 pi. So 2 pi over 8 really reduces to pi over 4. And that's the integral from 5 to 17. And u to the 1/2 du. So let's go about the integration here. Alright, so let's go about it. Let me actually put a box to this integral for a second. I'll tell you why later. Alright, so let's integrate to pi over 4. Integral from 5 to 17. Oh wait, no more integral. That we can integrate u to the 3/2 over 3/2 from 5 to 17, and that equals to, well, dividing by 3/2 is the same as multiplying by 2/3. So 2/3 pi over 4. Well, for now, let me call this u to the 3/2. I'll discuss about this in a minute. And that evaluated from 5 to 17. Well, so 2 over 4 reduces to 1/2, and 1/2 times 1/3, that's pi over 6. And well, so let me still do the u to the 3/2 from 5 to 17. Okay. Here is where we will have to take into consideration the different versions of the rational exponent. So this means the square root of u cubed, or this also means the square root of u, the whole thing cubed. Okay, we used the second version in the previous exercise, but in this case that's because we were able to compute the square root of a number because it was a nice number. It was a perfect square, and then we raised it to the 3rd power and to the 5th power. That's what we did in the previous example. Now let's analyze those limits of integration. 5 and 17, are those perfect squares? So in this case we won't be able to take the square root of 17 and then whatever we get, cube it, or the square root of 5 and cube it. So no, in this case we will have to use the previous version, the first version, play with the powers and take out the perfect square. So that's what we're going to do this time. So I'm going to go back to radical notation here. So that's going to be the square root of u cubed. And well, in this case, using the fundamental theorem of calculus, that's pi over 6 root of 17 cubed minus root of 5 cubed. Okay, well, in this case we will have to break up these factors. So 17 cubed is the same as 17 squared times 17, and 5 cubed is the same as 5 squared times 5. And in this case we would be able to factor out the perfect squares, so that means, okay, let me express the whole thing here. So that's pi over 6 the square root of 17 squared or times 17 minus the square root of 5 squared times 5. And well, let me highlight the perfect squares. So technically, what are we doing here in the next step? In this step, we're using the product rule for radicals, because here notice we have a product of two factors, that is the square root of 17 squared times the square root of 17. And well, what's the square root of 17 squared? 17 root of 17, which is going to be this quantity here, pi over 6 17 root of 17, and in the same way 5 root of 5. Final answer. Alright, final answer to this exercise. Well, half of the exercise. Okay, yes.
If you just multiply like 17 cubed and like in the square root, would they still take that on the test, or are they expecting us to pay the same?
No, to simplify radicals. The reason I go through all these details is, number one, that's what are we expecting on the exam, and also that's what WebAssign it would be expecting. I don't think WebAssign would take these radicals without simplifying. Yes?
You mentioned going back to the graph,
Yes.
and I
Let's
was
have a look.
thinking about that graph. Is this the area of just the outer?
Yes, just the outer. So in this case, we're not considering the top or the bottom. Just
and we're
the
also not considering the inside of it?
no, just the outside. So let's have a look at part B of the problem. Well, let me erase this to make some space. I mean, we already explained what this is. So part 2, functions of y. Functions of y. All right, number 1. What are we going to do here? So we have the function y equals x squared, and let's talk about the integral here. So the integral surface area equals 2 pi integral from c to d of r of y square root of 1 plus f prime of y squared dx. Okay, so let's find the derivative of y. Well, in this case, no, we're not going to find the derivative just yet because, well, number 1, this is supposed to be dy. Okay? So we need to have functions of y. And you know, that function that we're given, it's a function of x. So in this case, we need to solve for x. What do we do to get rid of the power 2 in this case? The square root. So that'll be x equal to the square root of y. But am I missing something? Okay, plus, technically we're missing that plus or minus, but in this case we can just leave it with the positive counterpart, and the reason for this is because we're working on the first quadrant where everything is positive. Had we been working with the entire graph, well, in that case we would have to subdivide this problem into 2 cases, the negative case and the positive case. So in this case, because again we have the we're working on the first quadrant only, this is going to be fine. Alright, so this x is actually our f of y. That's y to the 1/2, and the derivative, that's 1/2 y to the negative 1/2. And in this case, well, so that reduces to 1/2 root of y. It's important to reduce our derivatives. Don't leave it in terms of negative exponents, because these derivatives are going to be used to square and simplify stuff inside of the radical. Alright, so that's 2 pi. The integral, what about the limits of integration? Okay, let me go back to the top of the page. So in this case, we were given order pairs. If we were just given values of x, like 1 and 2 in this case, our job would have been to plug those values in the original function to obtain the corresponding y value. So in this case, for the integral in terms of y, these are going to be our limits. It's going to go from 1 to 4. And well, what about r of y? Well, notice in this case, this horizontal distance of x, that distance from the axis of revolution to any point on the graph, it's a horizontal distance, which is x. Well, in this case, this r of y equals to x, but our integral is in terms of y. That means we need to replace x with its corresponding function of y, which is this guy right here. Alright, so we're gonna go about the integral now. That's the square root of y times the square root of 1 plus the derivative 1 over 2 root of y squared dy. Alright, so that's 2 pi integral from 1 to 4 root of y. So let's square the inside, simplify the inside. That's 1 plus 1 squared, which is 1, 2 squared, which is 4, and root of y squared, cancel the radical with the square to get simply a y. And notice the space I left over here. That's because I'm going to combine these fractions together, and I need missing factors there so we can combine them. That is, multiply numerator and denominator by 4y, and that's dy. Put the two fractions together. 2 pi integral from 1 to 4 root of y times root of 4y plus 1 over 4y dy. So I'm going to do a couple of things in here. Well, I'm going to do one thing, number one. So we have the product of the radicals. I'm going to write this as one big radical and have everything as the product of y and this weird quotient here. So that's 2 pi integral from 1 to 4. That's the square root of y times 4y plus 1 over 4y dy. And this to cancel these y's together. Not the 4, the y. And 2 pi integral from 1 to 4. That's the square root of 4y plus 1 over 4. Well, in this case, dy, I'm going to use the quotient rule of radicals. The radical of a quotient is the same as the quotient of the two radicals, which in this case is 2 pi integral from 1 to 4, and that's the square root of 4y plus 1 over the square root of 4, which is 2. And in this case, notice how these two factors cancel out. So that's going to be pi, the integral from 1 to 4 of the square root of 4y plus 1. So let's do the u substitution for this integral. Alright, just real quick. U equals to 4y plus 1. Du equals 4y dy. That means the y will be 1/4. Oh, wait a minute, that's just 4, right? 1/4 du. And changing the limits, that's u of 1, u of 4. So this will be, okay, that's 4 times 1 plus 1, and 4 times 4 plus 1, that's 5, and 17 again. So 4 times 4 equals 16 plus 1, that's 17. And well, redefining this integral in terms of u, number one. Okay, let me go back to blue, and this will be, okay, pi integral from, instead of 1 to 4, that's from 5 to 17, and that's the square root of u du over 4. That's the same as pi over 4 integral from 5 to 17 u to the 1/2. Well, that's the root of u still. And let me box this integral because that's the same as this integral, right, from before. So we don't need to do all steps again, because what did we get in the end? Regardless of whether you use functions of x or functions of y, if you're rotating your region about the same axis, you should get the same result. And in this case, let's just go about what is it again? Pi over 6, 17 root of 17 minus 5 root of 5. Same result. The result changes, however, when you have the same region, but you rotate it about the x-axis or about the y-axis. And that's what we saw back in the first example. Well, actually, the first two examples, in which example number 1, we rotated the region about the x-axis. Example number 2, same region, but this time rotated about the y-axis. All right? Question? In which part? Which part? Second line right here? Right here. So this, okay, because by the properties of radical, that's the square root of a over the square root of b. Well, in this case, the square root of 4y plus 1, that's itself square root of 4y plus 1, but the square root of 4 is 2. Alright? So let's see. Actually, well, that's the end of the section. So let's real quick go about the beginning of the new chapter. So actually, this chapter is very short. And the next example, I'm just going to touch base on the definition of what differential equations are. Yes?
Just to make sure, this section is probably not going to be on the upcoming.
Yes. I'm not sure about section number 9.1. I have to check the calendar, but I'll let you know. All right. Okay, so modeling with differential equations. So what are differential equations? How do we deal with them? How do we recognize them? Well, number 1. Let me just give you the definition. And actually, the definition is a differential equation is that equation that contains whose unknown is a function, and it also contains some of its derivatives. Well, so algebraic equation versus differential equation. All right. So let's put something simple. Let's not make this too complicated. So x minus 3. Is that what I had before? Yes, x minus 3 equals to 5. Let's consider this baby equation here. Well, so whenever we want to solve an equation, we do both sides of the equation the same operation. I mean, in that, and what we do is the opposite of what we have to get the x isolated. So in this case, we need to get rid of this negative 3. We would have to do the opposite, which is add the 3 to both sides. All right. So that's going to give us x equals to 5. So in this case, what are we doing when we solve this equation? We're looking for the value of x such that when we subtract 3, we get a 5. So when you first learn how to solve linear equations in general, then you had to check. All right? What? Oh, yeah, that's what I meant, right? Yes. All right. A. Yeah. So check. I know, right? So check, and all we do is substitute our solution 8 minus 3 equals to 5. So 5 equals to 5, and whenever you got both sides of the equation the same result, that means indeed that's the result. Alright, what about differential equations? Let's do again something simple for now. So dy dx. So this differential equation can be recognized by having the derivative of a function in it. Minus 2x equals to 5. So what is this equation asking us to do? Well, they're asking us for the function whose first derivative minus 2x equals to 5. Well, so in the same way that we move things around in the algebraic equation, what did we do? Well, we left the variable terms on the left hand side, and the constant terms were moved to the right hand side. So in this case, what we're going to do, okay, let's first solve for dy dx. When we do that, that's equal to 2x plus 5. And then, now that we isolated the dy dx, now we treat this dy dx as a quotient of two quantities. And what we're going to do is have everything containing a y on the left and everything containing the x on the y, on the right side. So multiply both sides by the x, and dy equals to 2x plus 5 times dx. Well, so in this case, the result of solving a differential equation is not just going to be a number. Well, it's possible that it's only a number, but in this case, we are going to look for the function whose derivative minus 2x equals 5. Well, so we already did inverse operations. We added 2x on both sides. We multiplied dx on both sides. But well, in this case, we need to undo the differential so we can retrieve the original function. So what's the inverse of the differential? The integral. So we will integrate both sides. That's going to give us y equals x squared plus 5x plus some constant of integration. And this is our general solution. And the reason we call it a general solution is because this c can be infinitely many values depending on the initial condition. So let's check. So let's find the derivative, because our equation calls for the first derivative, and that's again 2x plus 5. So when we put this in the differential equation, 2x plus 5 minus 2x equals to 5. Well, cancel 2x with negative 2x, and 5 equals to 5. And again, this is a legitimate solution because when we check the solution, we get the same quantities on both sides. So what is this? What is it that we did here? What we did is to solve the differential equation by the method of separation of variables. So we're separating the y's. We're leaving the y's on the left hand side and the x's on the right hand side. And well, we're going to get into more details about this method of solution later. There's a bunch of methods to solve equations, but this is the only one that we're going to discuss in this class.
Why is it